Welcome everybody to today's ACM Tech Talk. These talks are part of ACM's commitment to lifelong learning. And our moderator today is Alex Kahn, while we wait for him, who's a strategic advisor, entrepreneur, and educator in quantum computing and AI. He's a visiting fellow at the University of Maryland National Quantum Laboratory and has also taught quantum computing at Harrisburg University. He's also the author of the book, Quantum Computing Experimentation with Amazon. You can find out more about Alex in the resources tab of your webinar console. So for those of you who are unfamiliar with ACM or what it has to offer, a few things we'd like to mention. ACM offers educational and professional development resources that bolster skills and enhance career opportunities. You can see some of the highlights on your screen in a moment. ACM provides access to the ACM Digital Library, the world's most comprehensive database of computing literature, leading publications and global conferences that draw top experts on a broad spectrum of computing topics, support for education and research, including curriculum development, teacher training, and the ACM Turing and ACM Prize in Computing Awards, and the ACM Code of Ethics, which is a collection of principles and guidelines designed to help computing professionals make ethically responsible decisions in professional practice. So before we get started, we just want to quickly mention a few housekeeping items. If you have questions at any time, please type them in using Zoom's Q&A button. We'll organize the questions as Charlie and Constantin speak, and we'll try to get to as many as possible. The session is being recorded and will be archived. You'll receive an email notification when it becomes available. And check learning.acm.org for updates on this and other upcoming webcasts. At the end of the presentation, you'll see a survey open on your screen. Please take a moment to fill out the survey and help us improve our Tech Talk. So again, today's presentation is An Elementary Approach to Quantum Computing by Charlee Stefanski and Constantin Gonciulea. I'm so sorry, Constantin, if I did not pronounce it correctly, and feel free to correct. Thank you. Charlie is a senior software engineer in the Advanced Technology Group at Wells Fargo, where she leads the development of the internal quantum computing platform. She holds a BS from the University of Michigan and a master's from UC Berkeley. Constantin is the head of cybersecurity, AI capabilities, and innovation at Wells Fargo, where he previously led the Advanced Technology Group. He holds advanced degrees in math and computer science. Over the last 25 years, he has delivered major server-side web and mobile online banking platforms and products, and has worked in quantum computing since 2018. Charlie and Constantin are both co-authors of the recently published Building Quantum Software for Manning and Publications. Charlie and Constantin, without further ado, take it away.
Okay, so we'll share some slides. And on the first slide, you'll see a classical machinery called the Galton board. I don't know if you are familiar with it. I have one here, a physical one. You can get it on Amazon or so. It has a number of pegs and a number of marbles falling through the pegs. I'll show how it works now. And at each peg, there is a equal probability of going left and right. And then what you end up with is the binomial distribution, right? Which is an approximation for the normal distribution if you want. This is similar to what we'll see in quantum computing. We get randomness from determinism, meaning that, the pegs are fixed, right? But every time you run an experiment, you get one of the possible outcomes. You don't know which one, but the aggregation will be a predictable distribution close to the binomial, right? So we have a video for that, but we don't need to run it because I showed this physically, right? So, and we'll post a link, some links to the videos as well. Next, if we look at the double slit experiment, if you are interested in quantum computing or quantum theory in general, you probably have heard about this experiment. Famously, Richard Feynman said that this experiment has in it the heart of quantum mechanics, right? Because it shows, so it goes like this. You have a source of particles like photons, same wavelength, like same color of light. And each photon or particle goes through one of two slits. They have to be narrow slits, right? In a wall. And then they travel some distance to a screen where we record where they land. It's called measurement, right? Quantum measurement. And what we see is an interference pattern that's specific to waves, right? And that's why, we talk about the wave-particle duality. So this is a little bit similar with the Galton board, right? You run the same fixed machinery multiple times, and then you get random outcomes, but they will follow a predictable distribution, right? And the single slit experiment is less known maybe, but it has all the elements that the double slit experiment has. Some people say it's not interference, it's diffraction. But still, you see this pattern where there are some spots where you don't get any particle, and then farther away you get some, right? So there is this wavy shape, and if you know about the discrete sinc or the sinc function in signal processing, that's what the shape is. And what's essential here, we have a quantum system, right? So the particles together with the slit and the screen and the wavelength of the particle matters, right? Together they form a quantum system. It has a definite state, and then you repeat the measurement on this quantum system and you get different outcomes. Key concepts here, we have outcomes with probabilities, and we repeat an experiment, right? And we get one of the possible outcomes. Now, if we formalize this, one of the big insights in quantum mechanics, when it was developed, the beginning of the previous century, and it took a long time to get the axioms or the essence of quantum mechanics. So it's very simple. The state of a quantum system can be described with complex numbers, one for each possible outcome of a measurement, right? So we replace all that machinery or apparatus, as Feynman calls it, with just a list of complex numbers. And now as computing professionals, we know how to deal with the list of complex numbers, right? We don't even need matrices. You'll see that, right? So let's have a refresher for what complex numbers are, in case you forgot, and it's pretty simple. They are called complex, but they're not complicated. So a complex number is a pair of two real numbers, called the real and the imaginary part. And if you take the point with those coordinates, you put it in a plane, then you have a vector from the origin to that point. So you can look at the complex number as a vector as well. You can see it as a vector as well. And then the distance to the origin, or the length of the vector, or the magnitude of the vector, we denote it by r, and we refer to this as the polar form. And then you have an angle from the positive x-axis to the vector, and that's called direction or phase, typically in when we talk about complex number. Now, if we superimpose that vector on a color wheel, we do this in the book. So the book is relying on this more compact notation where we use the color to indicate the direction, and then you get a simple color bar, right? So we save some space, but also I think it's visually appealing. And once you learn the colors in the color wheel, when you see, for example, if you see a red bar, you say, oh, this is close to a real number, right? It's on the positive real number on the x-axis. If you see a blue one, it's a negative number, right? So it's interesting. And in the end, it's also some math for colors, right? Okay, so let's go to the next slide after this refresher. In the book, we expand the complex numbers, the amplitudes for each outcome, to what we call a state table, right? So we show the outcomes and the amplitudes, the complex numbers associated to them, but we also add the binary representation for the outcome, the direction or phase of the complex numbers, the magnitude, and the color bar. So when you look at a quantum state this way, you get a lot of information, right? And this is one of the main ingredients in our book. So we represent quantum states as tables. And this is sort of a bridge between math and computer science, let's say, because we are used to lists and tables in computer science. And instead of talking about Hilbert spaces and bracket notation and so on, we just use the table. So it's an in-between that's also visual. Next slide. So it's also convenient to use an intensity instead of the length of the bar. And then we have what's basically a pixel. So we have a color with an intensity, right? And then the quantum state becomes a row of pixels, right? That's an image. Or you can break this long row into multiple rows, and then it becomes a two-dimensional image. And if there is one takeaway from this presentation, is that any quantum state is an image, right? So, because it's complex numbers. There are some constraints, so I skip this, that, you know, the square lengths of the complex number have to add up to 1 because the square length is the probability of that outcome. But any quantum state, you can visually represent it as an image, right? And it's almost the other way around. Any image, you can convert it to a quantum state, because if you normalize the intensities, you have to deal with black and white because we don't have them on the, that's amplitude 0, right? Or some convention, but a quantum state is an image. And then it's very, you can deal with quantum computing in a more elementary way if you do this in a more visual way. So we'll see how that goes when we go into so far we talked about quantum theory in general. Now we go into quantum computing. How do we use quantum systems to compute? And for that, we need quantum bits or qubits. This is one of the most common physical implementations, right? If you look at IBM doing superconducting qubits, or other companies use different kinds, but this talk will be about quantum systems that are made of quantum bits, qubits, right? And they are particles. The physical implementation will not be relevant. The same way, if you look at how your computer is implemented, if you are a programmer, you write code, you don't know about the transistors, right? The physical implementation is abstracted out. So the qubits are the same. They are physically there. But logically, what we need to know is that they are digits in the binary representation of outcomes. And they can be measured as 0 or 1, right? Which is similar to classical bits. And in order to make the transition to quantum computing, let's look at an alternative Galton board, right? But instead of pegs, we can use a binary tree, full binary tree. So each node has 2 children, right? And then each marble will travel on a path from the root of the tree to one of the leaves, and then it will fall into a bin. This implementation is also more efficient than the typical Galton board, because if you think of how many nodes you have, for how many pegs you have in the last row, if you have 2 to the n bins, you'll have 2 to the n minus 1. And then if you add all the pegs, there will be a lot of pegs. Here you have 2 to the n nodes, right? If you have n levels or 2 to the n bins. So that's a sort of alternative Galton board, which also captures the essence of a quantum computation, right? And instead of bins, we use our pixels, right? Intensities and colors, because complex numbers have also a direction, not only when you look at the bins, it's just how many. So it's a frequency. With complex numbers, we have also a direction, right? And we are representing the qubits you see there to the right as light bulbs, right? One per level of the binary tree. So you can think of them as, you don't know how they are implemented in a real computer, right? But logically, you can think of a qubit as a level in the binary tree. So when you do a measurement, you traverse the tree, and if you went left, it's a 0. If you went right, it's a 1, right? So the light bulb is on if it's a 1. And those are that's the binary representation of the outcomes, right, that we have at the bottom. You can break the single row into multiple rows, and columns. So you have a 2-dimensional image, and then you have 2 trees, one for the rows, one for the columns, right? So if you want to measure, you'll use the row tree to select the row, and then the column tree to select the column, right? And you end up with a position in the image. You don't get anything else from a quantum measurement. It will be always a position. If you repeat it, then you can create a grayscale version of the color image, which is the quantum state. You'll never be able to read the quantum state other than measuring one by one and getting in, a grayscale version of the image, let's say. Next, we'll talk about the fast Fourier transform. There is a very strong connection between quantum computing and Fourier transforms. And a refresher here, the discrete Fourier transform takes a big matrix and it multiplies a column of complex numbers to get another column of complex numbers, right? And that's not efficient. The fast Fourier transform that was created in the 60s, I think, last century, uses only 2x2 matrices. And actually, you don't even need those matrices. Most fast Fourier transform presentations, they use the butterfly pattern, right? So basically, you have multiple stages, and in each stage, you combine pairs of these complex numbers. In the first stage, you combine neighbors. You replace the pair by the first number will become the sum of the 2 numbers, and the second will become the difference rotated as a complex number. And that's the only operation, right? The angle of rotation differs, but in the second stage, the pairs will be 4. The stride will be 2. So, 2 apart. In the next stage, stage 2, they will be 4 apart, and then 8 apart, and so on, right? And the fast Fourier transform theory doesn't talk about digits, right? They only typically only the stride is used, the distance between the pairs that you recombine. If we want to connect it to quantum theory, where we use qubits, there is an equivalency. If you qubit 0 is the last one, right? So it will be neighbors, right? So branches that meet at that level, they will be recombined. That's an easy way to think about it. So each level is a qubit, and then for a certain qubit, you can think of what branches meet there and recombine them, right? It's an equivalent way of thinking about the stride. And why is that important? Because if we go to the next slide where we talk about quantum transformations, a quantum transform, there is only one type of transformation in quantum computing. And that looks like one stage in the fast Fourier transform. So we have a target qubit, would give you the stride or a level in the tree. And then you use a formula, the gate formula, to recombine the pairs. You also have control qubits that allow you to spare some pairs from being recombined, right? So you have some limit to this immense power of recombining all the pairs, right? But this is the only transformation, state transformation in quantum computing using the butterfly pattern. And we can visualize it with, if we use an image, you see the same butterfly pattern. If the target is qubit 0, we get neighbors being combined, neighbor rows. If it's target 1, we get rows that are 2 apart. And the same for columns, right? Depending on where the target is, you'll need, if the stride is bigger, then you get into columns from rows, right? But this is the only, so again, the second takeaway from this talk should be any quantum transformation is a butterfly pattern, which is the same as the one used in fast Fourier transforms. And you can think of it as rows or columns recombined. So I think we need to move a little bit faster. So in the next, I think, Charlie, we want to show this. We want to show, before going to this slide, can we show on a state table what the transformation looks like?
Yes. Sorry. So, we will, of course, provide all of these links. They're also in the slides that will be shared after the presentation. But our friends Naren helped take the functions that we developed for the book, the code from the book, and write some JavaScript to allow for these sort of little interactive modules to accompany the material in the book. And so we can look at just applying transformations to a quantum state. So here we have 3 qubits, and we have all of our elementary quantum transformations or gates. And so we can pick, we'll do an X gate, apply it to target qubit 0, and I can step through the transformation. We can see each pair. And let's see, let's do a Adamard gate. Let's see, let's do target qubit 1. And so now we can see with my target qubit 1, my pairs are 1 apart. And I can step through the transformation. I can also start with a random quantum state. So we can see now if I do an X gate, let's do target qubit 0 again. So now we will see, as we step through each pair, we will see the amplitudes switch. Yeah. So this will be available after the talk for anyone to play through or to play with themselves.
So I saw some questions about, is this a JavaScript model? Yeah, so the book uses Python, but we have a JavaScript version. We have also a Rust version that Savelli Yusufov created. It's called Spinoza. We can show that. Obviously, that's super performant Rust. And we use that for various simulations that we needed. And we extracted from that implementation, we extracted the fast Fourier transform in a separate project called FastFT, because when I mentioned the difference and the sum, that's the Hadamard gate. So the fast Fourier transform uses the Hadamard and the phase gates, just 2, right? And we were able to, I think we were beating, in some cases, not in all cases, most of the implementations on CPU for fast Fourier transform, right? So, and avoiding big matrices and working with pairs. That's key in fast Fourier transform. It's also key in quantum computing. You don't need big matrices, right? Now, if you do research, of course, you want to use all linear algebra, Hilbert spaces, and so on. But if you are a computing professional, just applying quantum computing, you really don't need that, right? So quantum computing, we're saying, needs its FFT moment, where we move away from these big matrices and to this more elementary approach. Okay, so let's continue with the slides. So why are we even interested in quantum computing? In the book, we mention what we call the two superpowers of quantum computing, namely one operation, one of these pair recombination changes all amplitudes, one operation, 2 to the n amplitudes, right? If you have n qubits, that's enormous power. You don't have that in classical computing, right? Now, it's also true that it's too much power. You need to limit it somehow. That's why you have, with entanglement, controlled operations, and so on. And the second is measurement, right? Any probability distribution you create using a quantum state, when you measure the system, you get an outcome. It's truly random, unlike the pseudo-random numbers we get classically, and also very efficient, right? There are some classically intractable probability distributions that are hard to sample from, right? Quantum computing gives you that sampling for free. It's called quantum measurement, right? So these two ingredients are the reason we talk about quantum computing now. And you can visualize both with the binary tree here, right? The pair recombination, which is applying a transformation, you recombine branches in the tree at some level. And the measurement is you go from the node to one of the out. You can think of it as a lightning, right? And lightning goes to different places, and then with some probability in this case. Okay, next, quantum Fourier transform. This is one important ingredient in many of the quantum algorithms, including the Shor's algorithm, right, which breaks RSA. And this is a match made in heaven between a quantum transformation, how it works, and the stage in FFT, right? So that's why this was 30 years ago. Quantum Fourier transform was used instead of FFT, giving a big advantage. A lot of Shor's advantage comes from this, right? And just to recall what the effect of FFT or QFT, quantum Fourier transform, is, if we take a single frequency signal, a periodic state, meaning that we have the same magnitude for the amplitudes, but their direction or phase increases by a constant angle from 0 to the last one. Then when you apply the inverse quantum Fourier transform, they are reversed for some reason. What is classically direct Fourier transform is inverse Fourier transform in quantum. So you get a representation of that frequency. In this case, the angle is related to this 4.7 times 360 over the number of outcomes. We recover this 4.7 factor. You see there in terms of probabilities, 4 has some probability, 5 has more. And there is a formula to tell you to recover that 4.7 from repeated measurements. And that's how Shor works. Plus, there is the Grover algorithm that increases the probability of some outcomes, and we'll not cover that in this short talk. And I think the last slide we have before going more into the tools and questions, function encoding, this is chapter 10 in the book. Shor's algorithm also uses function encoding for the exponential function. Here we use the polynomial function, and it's based on a paper that I had with Stefan Werner from IBM on encoding polynomials, right? It's very efficient. You see, if we have m qubits for input and n for output, the number of gates or operations is quadratic in m. It's not exponential, right? So here we're showing how you encode a parabola. And we'll show a video, actually, it will look like the matrix, but the quantum version. And we'll show also the identity, which is draw just a line. Draw a line in the quantum state. And we'll see how 128 points on the diagonal can be encoded with 96 operations, right? So each operation changes the whole quantum state, the whole screen. That's key. But you can do that classically. If you need to draw the graph of the identity function for 128 numbers, you'll need more than 96 operations, right? So we can show the videos, and then Charlie will go into showing some additional resources and then Q&A.
Sure. So let's start with the, let's see here, which one is that? Here it is, the parabola. So that figure on the slide, this is the video version, so it shows each step. So each time, let me just go back to the beginning. So each screen is one transformation being applied to the state. And we can see all 96 operations, and we end up with our encoded function.
Right. So that's why I was saying this looks a little bit like the matrix, but you can also see the advantage of using our representation of the quantum state with pixels, right, as an image.
And then we also have encoding the identity function. So same idea. Each change is one operation being applied to the state. And we can see we end up with the identity encoded in the state.
Yeah. So now if we go to chapter 10 in the book, you'll see why we start at 0, 0, and we go down. So that's why it looks a little bit different from your traditional identity. And the Python code to do this is in one of the Jupyter notebooks in the book. So all those screens, you can play with them.
Yes. So in the resources tab in the Zoom, the GitHub organization is linked there. And so you can get to most of the resources through here. And so the code repository directly accompanies the book. So the code is separated into each chapter. And then we have some additional resources. We already looked at the JavaScript, and we also have some more interactive resources in Code Plus as well. So this is the notebook that accompanies chapter 10, where we discuss function encoding. And so here we can see, let's see here, we're encoding the function, this function for inputs 0, 1, 2, and 3. And so, of course, in the book, it is explained how we represent this in this list of tuples. And so we have 2 qubits to represent the inputs, 4 qubits to represent the outputs, and we encode our function, and this is our resulting. This is sort of an adapted state table, more similar to the pixel images where we have we represent the registers of qubits with the columns and rows. And this next part gets into searching. And we have the identity in here as well, somewhere. Where is it? I don't know, but that's okay, because we can look at
maybe in chapter 12, but yeah.
We'll look at it here. So we looked at just the transformations module. We also have a function encoding module. So here I can do the same one that we had in the notebook. So 2 qubits to represent inputs, 4 to represent outputs. And we had x squared was -3, right?
You need
Oops.
to allow negatives. Yeah.
Yeah.
And again, this
And
is
here we go.
thanks to Naren Satish Kumar, UCLA student, who is helping with this with both Python and JavaScript. We want to form a community around the book. These resources are available to anyone, right? You can learn just by using them. The book will have more info, but there is enough. And can you show the tutorial, Charlie, just so, or the primer, we call it?
Yeah. So also from here, we have the primer, which I already have open somewhere here. So this is a quick interactive introduction that covers all the main concepts. So we have an introduction to complex number, refresher, quantum. We cover quantum state, and then single qubit gates, transformations, measurement circuits. So in here, we also have built in, thanks to the run, we have, for example, for the single qubit gates, so we can use a default state and apply an X gate and see the state before and after. It can do the same to just a random quantum state, apply an X gate. And so for each of the, I saw in the chat, some people were commenting that, of course, they don't know the elementary quantum transformations. It would take us the whole session to review each one. So I encourage you to just use this, right? And you can take your time and step through each one.
We chose
and of course, you also have the definitions in here as well.
Not to go through each gate, but all of them, the commonality is there is a different formula and they combine pairs, right?
Right. And then here we can, so that was a single qubit state to start. And then here you can apply the gates to multiple qubits, in this case, 3. Then we have controlled transformations and so on. So you can step through each gate, each concept, and build from single qubits to multiple qubits and so on. I think, are there any other, I want to leave plenty of time for Q&A. I know we're getting close. Constantine, is there any other tools that we want to make sure that we show?
We also have a quantum assistant that uses AI. So when OpenAI came with function calling in 2023, we created an assistant. So basically you can tell it, create a 3-qubit circuit, apply gate X to qubit 1, and it saves a lot of time. So basically you don't need an interface like what we showed, right? You can just talk to it directly. I think we are at version 3, thanks to Naren again. We don't have time to go through that, and it takes a lot of effort to update because there is so much new stuff in AI, right? New model, new frameworks, but it's there in Code Plus, right? And if we have enough audience, enough demand for it, we will update it. I don't know if Naren is in the audience, but he can say something in the chat if he is. And I think we are ready for Q&A.
Hi, everyone. Can you hear me? All right,
Yes.
good. Well, thank you, Charlie and Constantin. So let's move on to the question and answers. There's been a lot of questions going through both the chat and the Q&A here. So let me ask the first question. Most works in quantum optimization or quantum security tend to use QFT, for example, the Draper QFT adder or comparator. This technique is well optimized, but quite noisy when used on a real quantum computer, QPU, and not a simulator. What solution to this from a POV, I guess, point of view of a physician or a computer science researcher?
Physicist, yeah. You are breaking off there, but I think I got the question. So, as you know, we're not in production and will not be in production, anytime soon with quantum computers. As much as the manufacturers, they are pushing us to use the computers. So for using Shor's algorithm or for optimization, right? We have optimization in chapter 11. We do it on polynomials, right? So we can find maximum, minimum of a polynomial or find zeros of a polynomial. But that requires fault-tolerant quantum computers, right? We don't know how far away they are, but the group that we have and other groups, they are also looking at quantum-inspired algorithms, where we use just using complex numbers with neural networks, for example. And there is a group at Stanford, Hazy Research Group, that does that, right? So you have both directions. One is built towards fault tolerant, but meanwhile, let's see if we can use the ideas of quantum computing with simulations. We don't have the measurement though, so that's a big problem with classical simulations, right? Measurement is missing, right? So short answer is we'll need to wait for applying this in production.
All right, let me ask the next one by Duke. Can you explain the role of quantum gates in programming a quantum system versus logical gates in classical systems?
Charlie, you want to take that?
How should traditional software engineers intuitively think about quantum programming?
Yes. So quantum computing is similar to designing an algorithm like FFT. It's not, writing for loops, if statements, or designing a neural network, a new neural network, right? That's quantum algorithms. So at this stage, maybe later it will be higher level. Charlie, anything to add?
Not necessarily. I would say think of them in a very similar way, right? There are fundamental or most ground level or basic computing instructions. I did see in the chat earlier on someone asking about how familiar one needs to be with these elementary transformations. And in the future, if there will be higher levels of abstraction as we see in classical software development, right? And the answer is yes. There are already lots of work, lots of different Python libraries to make it easier to write programs for quantum computers. But because it's still at such an early stage relative to classical computing, it does require a little bit more familiarity with the most basic level instructions.
For a while, I know CRISP and I think Classic, they are trying to build more higher level languages even. But
Yes.
let's think about what happened with neural networks. Do we have anything like high level and a neural network will be created for you? Not yet. We need to design it from scratch, right? So it can, for some things you can do that, for other things, probably not.
All right, very good. So this question is for Charlie, and Charlie, you can answer as much as you can because it's a question with Wells Fargo in there. Wells Fargo's quantum readiness work highlights risk analysis, portfolio optimization, and cybersecurity. Which proof of concept has shown the most significant ROI signal so far?
So
And how
Charlie,
did you measure it?
we can talk about what's public, right?
Yeah, general public,
yeah.
yes.
Because the papers are public. Yeah.
Right. The use case that we are most focused on right now, we're excited about, is approaches to financial time series modeling. So generative models for limit order book prediction. In terms of the highest ROI, I'm not sure how to answer that.
We're not in production yet.
Constantin, what would you say? Yeah, I don't want to. It's a difficult one to answer.
Yeah. So what's important is to become quantum ready, right? We want to be ready when the production computers will be there. And Charlie mentioned the limit order book, right? That's one area where, again, this is public and there are talks, Vanya Markov talks about this, where you get a more expressive model using quantum algorithms than classical. So you get fewer states that you need to deal with, right? But in terms of implementing, we use simulators, and we want to be super efficient. So we use a lot of classical computing. You can call it high performance computing, right? And that's why we had Spinoza, using Rust, make it as fast as possible. Distributed versions we were working on, and depending on the priorities, we go back to that. But yeah, the important thing is that you need to understand the concepts. You don't need a lot of math if you'll do quantum computing as a developer, and that's what the book is. The target is developers, right? You can just use this high school level math, right, which is complex numbers, and that's enough.
All right. Okay, very good. So I think Constantin would love answering this question. This is probably what the book is about as well. So what is the difference between QFT and fast Fourier transform?
So QFT is a quantum version of the fast Fourier transform, and it's much more efficient. It uses exponentially less operations, right? So quantum advantage is about the number of operations, not it changes the same numbers, right? But with one operation, you do, with two operations, you do a full stage in FFT, right? So that's so they accomplish the same goal, and we have the FFT in the book, and we compare. We do a search to make sure that we get the same numbers, right? So, but it's much more efficient, and that's where the advantage, quantum advantage, many algorithms comes from. And if you think about it, nothing like it has been created in 30 years because people ignore this. This was just a match, right? QFT, direct translation, is how quantum gates work. But since then, nothing close to it has been discovered, like QFT or Shor, right? Because people talk about big matrices, Hilbert spaces. So at some point, when production-ready computers will be available, I suspect that computing professionals will pay more attention, and you'll see signal processing, probabilistic probability, let's say, understanding, playing a bigger role than Hilbert spaces, bracket notation, and so on.
All right. We have a question here. What would be the impact of quantum computing on software engineering field?
I would say the same that high performance computing has now, or neural networks. So some experts will work on it, 100% of their time, but not everyone. You'll not have a quantum computing quantum laptop, right? So it will be a center somewhere like high performance computing, and you'll send some computations there. It will definitely be hybrid, right? So you read the outcomes, you process them, you send another computation, variational versions, right, of computing.
Okay, so I've seen a number of questions between gates and measurements. So I think this question probably would help in clarifying maybe a confusion between what a gate is versus what a measurement is. So the question is, can we say that comparison of amplitude pairs is a coherence measurement that allows us to test the prediction of one of the signals by using the other?
I think that's part of quantum tomography when you want to discover the complex numbers in the state, but that requires a lot of measurements, right? So we can that's what the quantum Fourier transform does. It converts difference in phase in different magnitudes, and we have that in the book as well. So we call it that, converting from one to the other, right? So difference in phase tells you where the complex number is, right? And then you convert it to magnitudes, you do a bunch of measurements, and you can infer what the phase was. Quantum phase estimation, frankly, that's what it does. So yes.
All right. Okay, so another question, what common myths about quantum programming do you still see? And how does your book challenge and clarify these misconceptions?
Charlie, you want to take that? By the way, Charlie came out pretty much out of college, and she started learning quantum computing, and then she worked on the book. And she's so for young people out there, students, you can ask her about her experience in general. But yeah, Charlie, you want to answer the question?
Sure. I think there's more over hype than there are myths. Because many of the statements in the news and such are true, but with a lot of limitations or very maybe far out in the future or with the assumption that a certain caliber of hardware will be available at a certain point in time, which is a little bit of a gamble. So I would say that our book, we clarify, we make an effort to clarify what our good problems or appropriate problem spaces that quantum computing can address, at least now, and what maybe aren't, or because they're not feasible, or just because it's not necessary, right? Like it would make more sense to solve such problems on available classical resources. So that is, we separate them into 3 types of problems, and we try to really point out problem areas that make sense for quantum computing.
Also, we try to stay away from controversies. Like, you know, some people say the quantum theory is incomplete. Measurement doesn't make any sense. But with qubits, you just see it works, right? So we don't care what quantum measurement is in general and what it means for gravity. Or you can see, you have a quantum computer. We work with IBM computers. We used to use Honeywell and so on. So you see that the axioms work, measurement works, right? So it's not controversial. Even quantum parallelism, I think one of the reviewers said, oh, you shouldn't call this quantum parallelism. We call it parallelism because it's computing parallelism. It changes all amplitudes at once with one operation, right? That's parallelism. But if you go into parallel universes, and so we try to stay away from controversy and just focus on the computing part.
Okay, we are kind of running out of time. I will ask this question, and I might paraphrase it a little bit, but this is around quantum machine learning. So the question talks about QNNs and DQNN. Basically, I mean, how would you view AI machine learning as a path to accessibility to quantum computing as a pipeline framework can be fixed and the real programming is training?
There is a lot of research there. Maria Schuld from Xanadu, we really like her papers, and she emphasizes the quantum Fourier transform a lot there, right? But it's a field that's developing. There is some inspiration if you look at the transformers and the attention mechanism where you have positional encoding. Those are complex numbers, right? So there is inspiration both ways, and there will be a lot of developments in this space. But our book, we thought about adding a chapter or 2 on that, but we try to, again, keep it simple, elementary. We'd have had to add a lot more math to do that.
All right, I think we are out of time. So I really apologize. There's a lot of questions that came in, and there's further in the chats, but unfortunately we have limited time here.
Ping us on LinkedIn, or if we get a list of questions and the way to reply, we'll do our best. We have this site learnqc.com where we have information about the book. Again, we're trying to build a community. Maybe we'll add a section there.
All right. Yeah, so I'd like to thank Charlee and Constantin again for their informative presentation and insightful answers to the many questions. A special thanks to each of you for taking the time to attend and participate today. This talk was recorded and will be available online shortly at learningacm.org. You can find announcements on upcoming talks and other ACM activities at learning.acm.org and acm.org. Also, please fill out our quick survey where you can suggest future topics and speakers, which you should see on your screen in the moment. On behalf of ACM, Charlee, Constantin, and myself, thanks again for joining us, and I hope you join us again in the future. This concludes our talk.